All right, we're going to be talking about exact differential equations. Okay, so here's kind of an idea from Calculus 1. If you know that the derivative of y with respect to x is equal to 0, what does that mean? If the derivative is 0, that means that y is equal to some constant. Right? Okay, so that idea we need to kind of keep in our brains here because that's going to come back and be important. Another thing we might remember is implicit differentiation. So say I wanted to take the derivative with respect to x of something like x squared plus xy squared, say. So if I took the derivative of that with respect to x, that would be 2x plus, then I'd have a product rule going on here. Because x is, if I'm taking the derivative implicitly, then that means that y is also depending upon x. So I'm going to have to invoke product rule here. So I'll have 1 times y squared plus x times 2y dy dx. Okay, and one thing you might notice is that I have this part that doesn't have a dy dx, and then this part that is multiplied by dy dx. And you might notice, if you're a careful observer, that this part, the green part here, is actually the partial derivative of the function with respect to x. So this is the partial derivative with respect to x, and then this here is the partial derivative with respect to y. Okay, and so that's what we're looking for here. So if I had a differential equation that looked like this, 2x plus y squared plus 2xy dy dx equals 0, well, I mean, I just took the derivative of that function. What I can see is that this thing here, because this is the partial derivative with respect to x, this is the partial derivative with respect to y, this whole thing together is the derivative with respect to x of x squared plus xy squared equals 0. So what does that mean? Well, if the derivative equals 0 back up here, that means that the function is equal to a constant. So the solution to this differential equation is that x squared plus xy squared is equal to some constant. So there's your answer, okay? So say I had one that I wasn't sure about. Say I have the differential equation, let's make it complicated. So we have this other example. So say that I have y cosine x plus 2x e to the y dx plus sine x plus x squared e to the y minus 1 dy equals 0. Okay, so the question that we're asking is, does there exist some function and maybe we'll call it phi of xy, such that the partial derivative with respect to x of phi is equal to y cosine x plus 2x e to the y, and the partial derivative with respect to y of phi is equal to sine x plus x squared e to the y minus 1. So if this phi exists, this is called a potential function. Okay, and so we want to be able to know, like, does this potential function exist that has these partial derivatives? If it does, then our solution is just phi is equal to a constant. But how do we test? How can we tell? So the answer is that our mixed partials, our second order mixed partials, should be equal if such a phi exists. Okay, so if this is already the derivative with respect to x, I want to take the derivative of that with respect to y. So phi sub xy is going to be equal to, a lot of times we'll call this m and this n, is going to be equal to m sub y, which is going to be equal to, now let's take the partial derivative of that with respect to y. It'll be cosine x plus 2x e to the y. And phi sub yx, which will be equal to n sub x, I could take the derivative of that with respect to x, and I will get cosine x plus 2x e to the y, and then plus 0. So since these are equal, I know that phi exists. Okay, and so what I know then is that this is the partial derivative of phi with respect to x, and this is the partial derivative of phi with respect to y. So I can just pick one or the other and integrate it with respect to x or y. So let's take the one that has the most terms in it, because that might be the one that would give us what we want the best. So if I integrated sine x plus x squared e to the y minus 1 with respect to y, what I'm going to get is y sine x plus x squared e to the y minus y. So this is my phi, but I might also have some h of x that I haven't considered. So the partial derivative of phi with respect to x should be equal to m. So if I do that, the partial derivative of that with respect to x, so it'll be y cosine x plus 2x e to the y, then that'll be 0, and then that'll be h prime of x. And I want to set that equal to m, which is y cosine x plus 2x e to the y. And so that tells me, so h prime of x is equal to 0. So therefore my phi is equal to what I thought it was, y sine x plus x squared e to the y minus y. So our solution is, to the differential equation we started with, is phi equals a constant. So it's going to be y sine x plus x squared e to the y minus y equals c. So there's the solution to our differential equation.